In this video, we'll be looking at heat transfer, phase changes, and how drawing a heating curve might help us to organize our work in doing these sorts of problems. The first question reads, an 8.5 gram ice cube is placed in 255 grams of water. Calculate the temperature change in the water upon complete melting of the ice. What we want to do here first is figure out the amount of energy that it takes to melt that ice. And we know that energy is going to come out of the water. So this will be a two-step problem for us. To begin our problem, we're going to consider those 8.5 grams of ice that first need to melt. What I'm going to do first is convert my 8.5 grams of ice into moles. I'll do that by dividing by the molar mass of water. Then I'm going to multiply that by 6 kilojoules per mole. That's the delta H of fusion for water, telling me the amount of energy required to melt that quantity of ice. That calculation gives me a value of 2.83 kilojoules. Again, the energy that had to come out of the water and go into the ice cubes, causing them to melt. At this point, I'm going to pivot to now considering the 255 grams of water. Here, we'll be using a Q equals mc delta T equation. We have the energy, that's the 2.83 kilojoules that came out of that water. Now I'm trying to solve for delta T. So my first step is to isolate delta T. Say that delta T equals Q divided by mc. Plugging in some values there, I get delta T being equal to 2.83 kilojoules, which is equivalent to 2830 joules, divided by the mass of my water, 255 grams, divided by the specific heat of water, 4.184 joules per gram per degree Celsius. Completing that calculation, we find the change in temperature of that 255 grams of water will be equal to 2.65 degrees Celsius. Again, in review, melting 8.5 grams of ice is going to absorb a certain amount of energy from the water. Absorbing that energy from 255 grams of water results in a temperature change of 2.65 degrees Celsius. The ice is doing its job and cooling down that water. Our next problem states that the human body obtains 1,078 kilojoules from a candy bar. If this energy were used to vaporize water at 100 Celsius, how much water in liters could be vaporized? Now, of course, this is not what candy bars are actually doing. They're actually providing you with energy to do the various processes that your body is doing, but this is a nice way of quantifying the energy available in a large candy bar like this. What I want to do is take my energy, my 1078 kilojoules, and the first thing I'm going to do is multiply it by 1 mole of water having a delta H of vaporization of 40.67 kilojoules. This will tell me the number of moles of water that I could vaporize. I'll convert that value to grams. Each mole of water has a mass of 18.02 grams. And finally, I'll convert that value to liters. Say that each liter of water has a mass of 1,000 grams. Looking at my units here, my kilojoules cancel, my moles cancel, and my grams cancel, telling me now the number of liters of water that could be vaporized upon absorbing this much energy. And that value works out to 0.48 liters. The final problem in this problem set deals with carbon tetrachloride, CCl4. The question says, how many kilojoules are required to heat 18.5 grams of carbon tetrachloride, CCl4, from a liquid at 13 Celsius to a gas at 114 Celsius? This is going to help, or writing a heating curve will help me with this problem. I'm going to set up my heating curve starting at the lowest temperature, which in this case is 13 Celsius. That carbon tetrachloride will warm until it reaches 76.8 Celsius. At that point, it'll begin to boil. Then, after boiling, it'll continue to warm until it reaches 114 Celsius, and the problem's over with. Sketching out my curve, I see a gentle rise in temperature to the boiling point. We'll see a plateau of the temperature at the boiling point, and then we'll see another increase in the temperature, reaching the maximum temperature stated in the problem. To label some things on here, there are two different states or two different phases of this problem where there is a change in kinetic energy. remember that temperature is a measurement of average kinetic energy. So if the temperature is changing, the kinetic energy must be changing. Therefore, there's one segment of this problem where there is a change in potential energy. To be very explicit about the states of matter, I have a liquid state of matter right there, a gaseous state of matter at the end of the problem, and in the process of boiling, there exists both liquid and gas in that sample of carbon tetrachloride. The way to solve this problem is to quantify the energy change required for those three steps and then to sum that energy change. So I'm going to go ahead and label these three stages as 1, 2, and 3. Again, we're looking for the sum of the energy involved in all three of those phases. To begin with, step 1, we know there's a temperature change. So this tells me I'll be using the equation Q equals mc delta T. The energy required for this stage is going to be equal to the mass of carbon tetrachloride, 18.5 grams, times the specific heat of carbon tetrachloride in the liquid phase, which is 0.865 joules per gram per degree Celsius, times the change in temperature. And here, the change in temperature we're concerned with is 13 degrees up to 76.8 degrees. That is equal to 63.8 degrees Celsius. Summing those things together, I get 1,021 joules, which is equal to 1.021 kilojoules. The next step is going to be the boiling step for carbon tetrachloride. I have my same mass of carbon tetrachloride, 18.5 grams. But because I'm given a delta H of vaporization in terms of moles, I need to convert my grams into moles. To do that, I can divide by the molar mass, 153.8 grams, and then I can multiply by the delta H of vaporization, 27.8 kilojoules per each mole of carbon tetrachloride that I want to vaporize. That will give a value of 3.34 kilojoules required to boil this carbon tetrachloride. The final step is another Q equals mc delta T phase. Here I have the same mass, continues to be 18.5 grams of carbon tetrachloride. Because I'm in the gas phase, there's now a different specific heat. The gas phase specific heat for carbon tetrachloride is 0.542 joules per gram per degree Celsius. And the change in temperature for just this phase is going to be 37.2 degrees Celsius. Again, I'm calculating that because we're starting at 76.8 Celsius and going up to 114 degrees Celsius. Completing this calculation gets a value of 373 joules, which is equal to 0.373 kilojoules. At this point, I have the energy required for all three stages of my heating curve. And to get the total energy, I just need to sum those three stages. That is to say, my total energy is equal to the energy of step 1 plus the energy of step 2 plus the energy of step 3. That's going to be equal to 1.021 kilojoules plus 3.34 kilojoules plus 0.373 kilojoules, which is equal to 4.73 kilojoules. That's the total energy required to take my sample of carbon tetrachloride, heat it up, boil it, and then heat that gas a little bit further. Thanks for watching.